For decades, scaling a network meant writing manual routing tables and provisioning static servers. Today, those practices are a liability. When traffic spikes and a system metric crosses a designated threshold, modern cloud infrastructure dynamically expands on its own, drawing raw compute power from across multiple isolated data centers in milliseconds. This is the core requirement of high-availability engineering. Your architecture must monitor its own health, automatically provision or deprovision capacity in response to load, and absorb massive traffic fluctuations entirely without human intervention. To achieve this, we have to look past the top-line concepts and dig into the orchestration engines governing these systems. We will start at the foundational layer of virtual machine fleets, move up the stack into containerized microservices, and finish by mapping the strict event scaling rules of serverless architectures. The analytical question here is not simply what these AWS compute models do, but exactly how they mechanically execute capacity scaling under the hood and where their physical limitations lie. Operating highly available infrastructure requires abandoning manual intervention entirely and mastering these rigid automated control loops. The base foundational layer of AWS compute elasticity is the Amazon EC2 autoscaling group, or ASG. An ASG has three rigid boundaries. Minimum size establishes a guaranteed floor. Maximum size acts as a cost ceiling. Desired capacity is the active target. The ASG is a self-healing controller. If an instance fails, it immediately terminates it and spins up a replacement. While you pay for the underlying virtual machines you launch, the autoscaling group controller itself is provided at no additional cost. To stamp out replicas, the ASG requires a launch template. It feeds the ASG necessary parameters: the AMI, instance size, EBS storage, security groups, and user data bootstrap scripts. When expanding, the ASG reads this template, so every new machine boots with exact configurations. Once the new instance finishes its bootstrap process and passes a preliminary health check, the ASG automatically registers it with your load balancer target group, opening the valve for active traffic. The launch template is the translation mechanism. It converts raw compute potential into active load-bearing architecture the exact second a scaling alarm triggers. The ASG does not evaluate incoming traffic itself. Its elasticity operates on a strict control loop driven by Amazon CloudWatch alarms. This timeline charts aggregate metric data across an active fleet. Engineers typically evaluate average CPU utilization, load balancer request counts per target, or aggregate network throughput. Here, as the fleet's average processor load hits 75%, it triggers the scale-out alarm. That alarm triggers your scaling policies, whether adding fixed instances, nudging capacity to maintain a baseline, or acting on predictive historical forecasts. Once a new instance is requested, the ASG enters a mandatory scaling cooldown period, defaulting to 300 seconds. During this precise 5-minute window, the ASG explicitly blocks any new scale-out or scale-in activities, regardless of what the CloudWatch alarm is doing. This delay provides the physical time required for the newly requested instance to boot up the operating system, run its initialization scripts, start the application processes, and begin processing active user requests. Without this block, the metric remains high while booting, causing the alarm to continuously fire and launch redundant, unnecessary instances. The cooldown prevents metric thrashing. Because this cooldown creates an unavoidable delay in elasticity, engineers must optimize their environments. Building custom Amazon machine images with software pre-installed bypasses long boot scripts, allowing you to safely reduce the cooldown window and achieve faster reaction times. This automated scaling logic is not limited to virtual machines. It maps directly onto the orchestration of containerized microservices running on Amazon ECS. ECS service autoscaling monitors the exact same patterns, utilizing application autoscaling to adjust active task containers based on aggregate CPU, memory footprint, or request volumes. If your containers run on physical EC2 hosts rather than serverless Fargate, you implement ECS capacity providers. When the service requests more containers but the current fleet lacks physical RAM, the capacity provider automatically bridges the gap, triggering the underlying autoscaling group to rack new physical hosts. ECS Rolling Updates use strict parameters. On the left, a 50% minimum allows terminating older tasks first, causing a temporary capacity dip. On the right, a 150% maximum provisions new tasks first, pushing capacity higher temporarily before terminating old ones, ensuring zero downtime. Dialing in these precise deployment percentages guarantees a seamless zero-downtime deployment by maintaining necessary compute reserves. Getting the math wrong guarantees accidental service degradation. For development teams that require automated environment provisioning without directly mapping network and cluster infrastructure, AWS Elastic Beanstalk acts as a managed orchestration layer. Internally, Beanstalk abstracts architectures into distinct environments. You can run synchronous web server tiers, complete with load balancers and autoscaling logic, or asynchronous worker tiers. Beanstalk manages updates through multiple strategies. All at once forces immediate downtime. Rolling flips in staggered segments. Immutable builds a temporary duplicate group. Blue-green builds a fully parallel environment and swaps DNS routing, while traffic splitting routes a tiny fraction to test stability first. Beyond managed platforms, you can manually build highly resilient architectures by decoupling your system layers entirely with Amazon SQS. An SQS queue acts as a buffer. Instead of scaling on CPU, a CloudWatch alarm monitors the approximate number of messages. When the queue fills, the alarm triggers the back-end ASG to rapidly scale out worker instances to drain the backlog. By isolating the compute layer behind an asynchronous queue, your infrastructure scales aggressively based entirely on pure message volume, insulating your application from volatile surges in direct user connections. As we push further into data planes and serverless architectures, the concept of a cooldown period disappears. Instead, systems execute against strict, hard-coded mathematical capacity limits. When operating Amazon Kinesis data streams in provisioned mode, engineers manually define a fixed number of shards. Each shard enforces strict boundary limits, precisely 1 megabyte per second inbound or 1,000 records per second. Any data pushed beyond those fixed limits is simply rejected. Alternatively, Kinesis on-demand mode eliminates manual shard planning, automatically scaling up capacity based on the highest observed throughput peak during the previous 30 days. When Lambda is triggered by streams, the event source mapping generates exactly 1 Lambda invocation per active stream shard. To increase throughput without more shards, engineers explicitly enable parallelization, instructing the mapper to process up to 10 concurrent message batches per shard simultaneously. Standard SQS queues utilize a totally different mapping logic. Because standard queues do not enforce message ordering, Lambda applies an aggressive scale-out rate, adding 60 execution instances per minute to drain the queue, scaling up to 1,000 concurrent batches. But if you use an SQS FIFO queue to guarantee the sequence of events, Lambda strictly throttles its concurrency. It will only scale out to match the exact number of active message groups, ensuring out-of-order execution is structurally impossible. Serverless architecture is highly elastic, but it is entirely governed by explicit API-level throughput quotas and strict batching mathematics that engineers must explicitly architect around. When mapped correctly, the entire compute plane operates as a cohesive unit, from massive physical host farms down to microsecond serverless event executions. Capacity adjusts constantly. We have traced the flow from rigid virtual machine boundaries through containerized deployments down to the granular execution rules of isolated queue mappings. At every tier, achieving scale requires managing operational state. You have to account for instance boot times, configure safe deployment percentages, and define strict batching logic to prevent system collapse. Automated orchestration transforms rigid infrastructure into a dynamic, responsive engine capable of self-healing under extreme load. But compute is only one half of the high availability equation. The processors and memory running your application logic ultimately rely on a persistent data layer. In our next analysis, we will map the mechanics of database resilience. We will break down RDS multi-AZ failovers, deconstruct the cluster storage engines behind Amazon Aurora, and explore high-performance caching nodes with Elasticache. Because a perfectly elastic, self-healing compute plane is entirely useless if the database beneath it becomes a fatal bottleneck.